Hi, everyone. Thanks for joining me. We've only got 20 minutes on the books, and we've got a lot of things to talk about. So whatever I don't get through now, feel free to just spend some time with me afterwards. But we're going to do a little whirlwind tour of things you should think about when developing a connector. So let's just quickly introduce myself. I'm Eron Wright from Dell EMC. I'm technical staff, and I work on a project called Pravega. Pravega is a stream storage system with some interesting properties that has taught us a lot about doing good connectors, and I'm a maintainer of the Flink connector for Pravega. Some of the things that Pravega does is a dynamically sharded system similar to Kinesis. It has a notion of event time tracking for generating watermarks that are correct. And it has transaction support to get an exactly once effect in your sinks. So what I'd like to do with you today is relay some of the lessons we've learned from building a connector that can apply those properties to Flink. So I'm going to cover some general things you should know about connectors, then just a word or two about the table API and how to think about building a connector for that, which I think is actually really important and valuable. As you see from the content of this week. Then we're going to spend some time on event time because the connector plays an outsized role there. And then finally, we'll talk about some of the state and fault tolerance mechanisms that you have to make use of to solve some of those problems that we identified in those earlier sections. All right, so firstly, just a word on developing a connector. Applications take a dependency on your connector. It's not built into the cluster. So you think of an application having its normal, Maven dependencies. They're linking to your connector. They're probably shading your connector into their application, to construct an Uber jar. And if you want to make life easy for them, I would consider even shading your connector's dependencies into your connector jar so that it's as easy as possible to incorporate that connector into the application. In other words, I would definitely suggest you not force the user to build a complex shading file that understands your dependencies, but try to encapsulate those. Where will you host your connector? Well, ideally upstream in the Flink repository, but there is some natural reluctance to have new connectors there because it presents an ever-growing test problem for the Flink community. So there is an external repository called Apache Bahir for Flink, where you'll see some additional connectors developed there that are technically not in the Flink repository. And of course, you could have your own repository as you like. There's different types of connectors, but they build on each other to some degree. As you know, there's streaming connectors. A stream connector might act as a source or as a sink. That connector might work with bounded or unbounded data sets. A bounded streaming connector, for example, might run out of elements to process, and in that scenario, your Flink job will wind down gracefully. It's kind of cool. Now, I won't say much about batch connectors today, but I want to point out a couple things about table connectors. Table connectors are, they act as both sources and sinks or even both, because when you think about a table might be something you're actually selecting from or writing to. So there's an interesting programming model there. I'll talk more about table in a few minutes. So when you are developing a connector, here's 4 things you really want to think about. 1, how will you parallelize your data source or sink, right? Which means subdividing that source data into partitions or something that will be assigned to operator subtasks. Ideally, you can support parallelism changes, since, as you know, a Flink job might change the parallelism over time for your source. Usually that's done by suspending the job, stopping the job, taking a save point, and then starting the job from that save point, and there a parallelism change might have occurred. And some of the state mechanisms that are in Flink are geared towards making that parallelism change possible and relatively easy to to do. Second consideration is fault tolerance. Obviously, you're hoping to provide an exactly once semantic. That's kind of the high bar that you would like to reach. It's easier probably on a source than on a sink. And you're supporting checkpoints and save points. Thirdly, how to support both historical and real-time processing. And this is a really interesting point that I'm going to get a lot more into, but the behavior of a connector in that historical processing scenario can be quite different than in the real-time scenario. The program is the same either way, right? That's our dream, that we have a unified programming model. But you do need to think about how your connector is behaving in that historical regime. And then you probably want to think about the security elements too. And I'll talk about some of the options you have there, things like credentials, which you'll probably have in any real connector. As for a connector lifecycle, like other functions, they're instantiated in the driver program. Right? So life begins in that main method of the user application. You'll probably, or I would suggest, providing a builder pattern for your connector there. So they'll construct an instance of your connector, and they're really configuring your connector at that time. And then your connector is being serialized as part of a job graph that's submitted to the cluster. During that construction phase, try to avoid connections to your data source. This is all actually happening in a program that's outside of the Flink cluster, actually. So focus on construction, not on actually making connections. All right. There's an interesting cancel and stop aspect to connector lifecycle. All connectors are expected to support cancellation, and there's a pattern that you'll see when you write your connector that you usually use like a transient running field. And then also that has some implications on event time. In particular, when the user is stopping a job, the user has an option as to whether to stop with the intention that this job is like never going to run again, as opposed to stopping and then going to be restarted from a save point that's being taken. And in that first case, the system will actually advance event time to the end of time, which will cause all of the intermediate state to flush out. So keep that in mind when you implement your connector. Next thing you'll think about is data types. Connectors are typically agnostic to the record type, and you typically accept a deserializer from the application code, right, to deserialize individual records in whatever way makes sense. In that case, you'll probably work with a type called deserialization schema, which is the interface that user code will implement to control how an individual record's deserialized, and you'll just want to work with that, whatever implementation they hand you. And you'll probably implement result type queryable, which is an interface that lets your connector advertise what the output type is without that being statically known. For sinks, likewise, there's a serialization schema. And it's interesting to point out that there is first-class support in Flink for a few different data types, Avro, Parquet, JSON. So your connector doesn't necessarily have to provide like a JSON deserializer or an Avro deserializer. A lot of that stuff is out of the box now. That would be hilarious. But to some degree, those are geared towards the Flink table API. So especially in that scenario, what you'll find is that the application code will give you, will probably make use of one of those out-of-the-box serializers. Another thing to think about is metrics. Flink actually has a cool metric system, and you can register new metrics groups. Highly suggest you do that so for your connector and whatever thing makes sense. When you wire up this metric system as a deployer of Flink, you can wire it to InfluxDB or Prometheus, or even the Flink UI displays these metrics. So my suggestion is, take advantage of the counters and gauges and histograms and the like that you can produce in your connector to give important information, like let's say about the lag or the current offset or what have you for operational reasons. Connector security. Keep in mind that credentials are actually ordinary program parameters. So if, let's say you had an S3 connector as a hypothetical, you would have S3 credentials being treated like normal program parameters, which are not particularly protected or safe. There is first-class support for Kerberos credentials if your external system is Kerberos enabled. And in that case, the Flink cluster gets configured with a key tab, and you, as a deployer, can control which what are called Jazz contexts, which is how Java works with Kerberos. You can control whether the connector will get access to that key tab. Just a word or two about the table API. It's evolving quickly. Usually, I think this is still true, that table sources and sinks are actually built on top of data stream or data set API. So by investing in sources and sinks at the data stream API, it's relatively easy to package those up into table sources and sinks. That has been historically the case. I think that's still the case. If someone nods or shakes their head, you can tell me otherwise. Okay. All right. Another thing you might want to do is make use of the catalog system that is, especially that's new to Flink 1.9. External catalogs let you register tables sort of in an automatic way. So if the system you're connecting to is relational and it has some notion of a catalog of sorts, it's now possible to expose that in a very nice way in Flink, and that could complement a connector very nicely, so that you get that SQL shell experience that just pops up and they can list tables and do stuff right away. All right. Glad that we've reached event time, because this is where probably most problems happen. Connectors play this critical role in program correctness. Why is that? Because though we want to give the user, the application, some control over watermark generation, the standard watermark generation techniques that we see in Flink today are fairly simplistic and rely on the order of observation of elements. A connector, especially one that is drawing from a sharded or partitioned system, actually has a lot of control over the order of observation of elements. If you think of a typical connector that's working against a partitioned source, for example, it could choose to schedule one partition before another, and thus the downstream watermark generator will actually observe all the elements from one partition and then all the elements from another. And I'll show you a diagram now to show how that can create chaos in a watermark generator, and as a result, can really produce corrupt program output. The second thing to know is that if your connector is intended to be used with event time, and it has a lot of, and there's like an abundance of data to draw on, it's worth investing in controlling the so-called event time skew, which means how far ahead some elements are in event time relative to other elements. And this is for efficiency reasons. There's some steps your connector can take to try to minimize that skew so that the system moves ahead in a regulated way with respect to event time. Just as an aside to show you how dynamic a data source might be, this is a Pravega stream, which is similar to a topic, and it's a highly sharded system. And I just wanted to show this picture because it's a bit dramatic. What this shows is actually one stream that's been broken down into a key space, and you can see each one of these blocks here is an individual shard or or segment of that stream. And over time, the system splits and merges streams, these segments, based on the demand that's being placed on different parts of the key space. That's how it achieves scaling. But if you think about your connector scheduling all of these segments, there's a lot of flexibility in the order in which these segments are ingested, even on a per subtask basis. And if we're not careful, we can cause havoc in event time as a result. I want to show you a diagram to help illustrate what I'm talking about. At the top, this is kind of an idealized case that we will usually see in a real-time regime. Here's an example where a source, but you can see there are 3 sections here. I just want to talk about the top section first. That top section, we have 2 partitions that are being drawn on by a particular source, and by that I mean a particular subtask. You can imagine that source drawing from the 2 partitions one at a time, like round robin. And so it would emit, 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, and so on as it drew on these underlying partitions, right? Now imagine you were writing a watermark generator for this. You've probably used something like the bounded out-of-orderness generator, something like that. That generator is probably going to work pretty well because it'll observe 1, 2, 3, and it'll probably be able to generate a reasonable watermark. But what if there was an abundance of available data and this connector wasn't designed to maximize this kind of output? Imagine that my source was developed such that it drained all of one partition before another. Or let's say that one partition is located on a different server than another, and so it's slow, like there's some network speed difference between these 2 partitions. In that scenario, the source might emit a lot of the purple partition, partition 1, before emitting some of partition 2. Now think about your poor user who's going to write a watermark generator. It'll observe what amounts to chaos. You can see, and you have to extrapolate, use your imagination, but you can imagine how you might observe partition 1 for some time before observing partition 2, and it might flip back and forth. And the net result is that the watermark generator, its heuristic will probably fail, and you'll probably end up generating premature watermarks that cause a lot of the records to be marked as late. This will essentially produce a corrupt program output. And so we need to take some steps to try to sort of avoid that situation. And this can happen in like a few different cases. One case is what I would call the historical processing regime. If you think about your connector working on a backlog of data, now eventually it'll hopefully churn through all that backlog and will have reached the tail, and now it's tailing the stream and is producing results more or less as they show up. As you get to that tail, you've entered a real-time regime, and then the output of your connector will probably resemble that top section. But in a historical regime, where there's an abundance of available data, we're much more likely to see the kind of chaos that's alluded to in the second diagram. And depending on the nature of your source, there's a few different strategies that we can use, and we're going to talk about in the next couple slides. One strategy that we see in the Kafka connector is to use a per partition watermark generator. And this diagram helps to make clear why that's actually very useful, because you can see by putting a different watermark generator instance on each partition and keeping the state tracked about the watermark that's produced by each one of those generators, as does the Kafka connector, then each individual watermark generator observes a rational progression of event time. 1, 2, 3, 4, 5. In this case, even an ascending watermark generator would work in this scenario. So this was, I think, a really good idea that Kafka does. The Kafka connector does, I should say. keep in mind also that this is a diagram right out of the Flink documentation. You can see how watermarks, which are the yellow boxes, how they progress through the data, through the graph over time as it makes progress. Basically, each source instance, in the case of, say, the Kafka connector, it uses the watermark generator on each source, takes the minimum of that, and that's what is emitted out of the subtask. And then that propagates like normal. But it's super important to keep in mind that once you make that assertion that, in this case, time 17 has arrived, there's no way to retract that assertion. So you need to be careful about how you're scheduling your shards or partitions. If you were to be scheduling, imagine you had a sharded system like we saw in that earlier diagram, and we were scheduling these shards based on a hash of their shard ID or something. It could be that you would schedule these shards across these two subtasks in such a way that event time would really jump back and forth quite a bit. But because of the inherent limitation of Flink, in that an individual subtask is assumed to have an ascending watermark that's relatively stable, the net is you'll produce late events and your program won't work, especially when you're in the historical regime. This actually presents some pretty serious challenges to a connector developer. But I just want to quickly buzz through some of the facilities that you have to work with to take advantage of to maybe compensate for that complexity. One thing that's new to Flink 1.9 is a global watermark tracker. What you can do now is the job manager has a global aggregates facility where each of your subtasks can actually publish the local watermark that it has observed and coordinate to establish a global watermark. And then your source will just publish the global watermark. So it's a way to actually coordinate your subtasks so that you establish a global watermark rather than a watermark that's scoped to your individual subtask, which might be necessary if you have like a highly dynamic system. So consider taking advantage of that. Take a look at Kinesis connector watermark tracker interface. This is new to 1.9. It's actually really, really helpful. I think it's solved a major problem in historical processing with Kinesis. Another thing to consider is what's called source idleness. There's a source idleness element there where if you think of each subtask as having a hold on the event time clock, each subtask is making an assertion about the progression of time. Okay, so subtask 1 and 2 saying, I think it's noon now. And this guy, oh, I think it's 11:55, or at least with respect to the data that's been emitted so far. If you were to not emit any watermarks in any one subtask, overall time would not progress. Yeah, I'm out of time. Overall time wouldn't progress. And as a result, the system will stall. Idleness is a way for a subtask to declare that it has nothing to say about time and actually relinquishes its hold on the event time clock. Don't do that for the wrong reasons. Don't do it because of a connection problem or something. You want that idleness to be a semantic, based in the semantics of your data. So, for example, the Kafka source doesn't or goes idle when no partitions are assigned to a particular subtask. When you relinquish your hold on the event time clock, that lets the other subtasks determine how time is advancing. And so it's another little complexity to keep in mind that if later you want to take a partition and assign to that subtask, it will be, the current time will have already been established by everyone else, so another complication. I think that's all the time that I have, but I'm happy to chat with you more in the speaker lounge. If I can now take some questions in the time that I have.
Yeah, I think we're running out of time, so if there are any questions, I think Eron will be happy to address those in one of the lounges upstairs. Thanks very much, Eron.
Thank you.